in considering resistance and resistivity, remember that resistance is going to be rho L over A. Okay. Well, remember we also said that rho, the resistivity, is going to be M over N E squared tau. Now, for most of this, is not a big deal. M is a constant. E is constant. For semiconductors, N can be a function of temperature. If you increase the temperature, you can get more conductors. You decrease temperature, you can decrease conductors. In fact, there's actually a type of semiconductor that this happens very linearly with, and we call it a thermistor. And so the resistance is going to be directly dependent on the temperature in a very precise manner. You increase the temperature, you decrease the resistance, decrease the temperature, increase the resistance. And so that means you can measure the resistance and measure the temperature with it. What I want to talk about here is the mean collision time. So we talked about what does that mean? That means your electrons are going along, they're bouncing off of things, and this is related to the average time between collisions. And so if you increase the temperature, all these atomic cores are moving around more, and so you increase the likelihood of a collision, which means as temperature increases, the mean free collision time decreases. So if the mean free collision time decreases, then clearly the resistivity increases and the resistance increases. So the resistance increases with temperature. So we can define the change in resistivity with temperature as rho naught times 1 plus alpha delta T, where delta T is going to be T minus T naught. Now, rho naught is the resistivity at some reference temperature. Frequently, the reference temperature here is going to be at some temperature like 0 or 10 degrees Celsius or 20 degrees Celsius or something. Most engineering applications are 20 degrees Celsius for some reason. But you can make anything you want as long as you measure what it is at that temperature. But if you look it up, it's normally 20 degrees Celsius. Alpha is the temperature coefficient of resistivity. That's how much it's changing. And then if you're measuring this here, then you need to keep track of what units that is. Usually that is in inverse Celsius degrees, and so the T would have to be measured in Celsius. And so that gives you the resistivity. We know that R equals rho L over A. Now, typically, the length and the area don't change appreciably with temperature. At least they don't change nearly as much with temperature as does the resistivity. And so we can then approximate that the resistance at some temperature is R naught. Okay. So that means that we have